Quasim Zaidi from SUNY. He's a distinguished professor there. Quasim has been mainly working on color perception and form perception. And that's the relevance to Jan's work. He and Jan have been knowing each other and knowing each other's work for decades. Quasim got his PhD from, I'm sorry, I forget right now. Chicago, right. I'm sorry, I had the senior moment. And I would say, I don't want to say many things, but you see his work is quite computational along Jan's lines. One thing that I would like to mention is that Quasim and I crossed paths back in Bell Laboratories when he was a postdoc of John Krauskopf, and I was working with Bela Judas when we were actually much younger than we are now. So his talk is geometry and perception.
So Tony's always a hard act to follow. So I said, so what could I do? I could do something different. So I could look for things which were actually directly inspired by Jan, instead of trying to find things that Jan hadn't done. So this really is, I must admit that the first paper in visual perception that really exercised my imagination in graduate school was Jan's paper, essentially using Helmholtz's theorem to divide up optic flow into solenoidal and irrotational parts. And years later, Uncle Jane was sitting behind Jan, and I actually exploited that understanding deforming objects. But this is going to be simpler stuff. And this is going to be in two parts because it's homage to two parts of Jan's work. So the first part was actually done by Erin Cook, who is sitting somewhere here, back there. She raised her hand. So one of the things we do very well, and which is very important to do, is to judge poses of objects in the world. And this is not so easy. Do we have a pointer? Yeah. So here is a simple object made out of two Legos at a 90-degree angle. And when you're looking at it like this, it looks like a 90-degree angle. And this is the same object, but when you look at it, so if you look at it from here, it becomes like this, and it now may look to you like the angle is slightly obtuse. Whereas if you go here and look, now it starts looking like the angle is slightly acute. And it's exactly the same 3D object. But even 3D objects, depending on where you look, can look distorted. It becomes more interesting if you take, say, one of these pictures and use it as a picture and look at it in three different viewpoints or three different slants of the screen. So this is the same as here. And now you will notice something quite interesting, which is they actually look a lot more alike than they do here. And more interestingly, that this one keeps pointing at where you're looking. Because if it were to go with the screen, it should be pointing out of the screen like it is doing over here. And this is the classical pointing out of the picture phenomenon, and Jan has worked on it. This isn't just true for simple objects. If you take more complex objects, when we did this experiment, these Barbies didn't have clothes on them, but we got censored at VSS. And the lack of clothes was also an homage to Jan. But it actually is a completely innocent 3D rendition of a painting by sort of Perlstein, which looked to us was changing a lot when we looked at it from different viewpoints. So we made the 3D version of it. And again, when you look at it, it's just this one single 3D configuration from different viewpoints. Here, they look like the two bodies that are obtuse angle. Here they're 90 degrees, and here they're sort of slightly more than 90 degrees. So again, the relative poses change from where you look at a 3D object. And again, if you take the center one and look at it as pictures from 3 different places, you again notice that this torso keeps pointing at you. And what you may notice when you compare, this is easier to do here, compare these to this, is there is some distortion of sizes depending on what's closer to you and what's further away from you here, but it's a lot less distortion than there is here. So poses are less distorted here. It's almost as if the whole scene rotates towards you, but the relative sizes are very distorted. So the legs are much larger than the head here, and the head is larger than the legs over here. So we wanted to understand this, but what goes on here? So we made simple objects out of Legos, single ones, acute, right, and obtuse angle ones, and they were presented on a vertical screen, and the observer had this horizontal screen in front of them, and they could rotate this vector, and for each of the limbs, they could then tell us what the pose of the in 3D was on this thing. So you're looking here, and you're making a pose of what it would be like in 3D, even though you're seeing it like that. And the first one I want to talk about is when you're looking right from in front. And so these Legos, you could think about them, we could rotate them in about 16 different steps. This is identical to whether you moved yourself or whether you rotate it. And we were looking at it right from the front. So in a sense, even though you're looking at it on a screen, it's like seeing the 3D scene through a window. And the projective geometry of that was worked out eons ago. And what happens is, so this is the ZX plane here, I'm sorry, X and Z plane here. And so if something is lying on the ground like that, when you project it up, you can see the circle gets distorted and gets more distorted here than here, and this changes a bit of orientation here. In fact, this is the simplistic equation you get out of it. And the interesting thing is if you plot the rectal 2D orientation versus the physical 3D pose, what you will notice is that what's 90 degrees here that's pointing towards you or 270 away from you is also 90 and 270 here. And also what's 0 and 180 here will plot to 0 and 180 here. The other things have this almost sinusoidal modulation around this diagonal. And the nice thing about working this out is that if you present things on the ground and the person can assume that they're on the ground, then they could just do the back projection to get the poses right from the rectal projections. So this is just a back projection of what I showed you before. This is a rectal orientation of physical 3D pose. Notice again that 90 in the rectal orientation should be seen as 90 in the physical 3D pose, 270 here, and 0 and 180, but the others should vary a bit. But if some machine were to take rectal orientations, knowing that everything is on the ground, and apply this back projection, they would get the poses just right. So this is the same back projection function I showed you, and this is the average over a lot of observers of doing the experiment that I showed you. And you can see that there is this little wavy line, very much like this, and the nice thing is the 90 degree thing is seen exactly right, so it's 180, so it's 270, and so this is what's happening. When you compare the perceived distortion, which is this minus this versus the physical pose, you see that there's actually quite a bit of distortion. So this is going up to almost 35 or 25 degrees over here. And this goes along with what I was showing you first about when you're looking at the same 3D scene from different views, you can get lots of distortion in what you see. And the one difference that you will notice is that this is shallower modulation around here than this is. And this tells you what's going on, which is when you're between 0 and 90, you're actually seeing it as less. And so essentially what it is you're seeing things as more frontal-parallel than they actually are. And that's systematically true for all of these intermediate things. Now, why you see more frontal-parallel, I can talk about that later. We've got 3 conjectures, we don't have any answers yet, but that's all there is. So, to model this, all we did was put this one parameter k in this back projection function, and what this does is it makes things go more frontal-parallel, and so this is this function fitted to the data. This is the root mean square. We're not presenting r squareds because r squareds for nonlinear fits way overestimate. They're usually around 0.99 anyway. And this is the factor 0.55 over here for the averages. It also pretty nicely fits this perceived distortion. So, okay, so we now have a good idea of what people are doing. They're using something very much like the back projection, and they've got this frontal-parallel bias, and that seems to describe what they would do in a 3D scene. So then we were curious as to what would happen if we took the same thing as pictures and changed the position of the observer. So the screen stays here, but the observer sits in all these different positions. And now there's one more thing. So if this was the picture plane seeing frontal-parallel, now when you go to the side, things change a bit. Now this axis gets a little compressed, and in some ways this gets closer to what it originally was. So that's there. And so you get the same, so now you have this function. So you get the same back projection function, but it's got a shallower modulation over here. And we can calculate that for, sorry, I was wrong. This is the forward projection function from physical 3D goes to retinal to the orientation. And this is the same back projection. So this is now we take the back projection function, assuming that things are on the ground. And as you can see, they have the same sort of modulation, but they shift. But the 90 degrees are at 90, 270 and 270. And so if people could look at the slant of the monitor and discount it and apply the proper back projection functions, this is what you should get as the perceived poses. But we're going to take a different hypothesis. We're going to say that what people do in 3D scenes, they apply the same back projection as for the actual scene, which is this one here, even though the retinal orientations have been changed. So here are the 5 back projection functions. Here are the average data. And what you will notice is, yes, they have the same modulations, but they're shifted. And this shift is exactly equal to the viewing angle. And so what this is exactly almost perfect rotation to the viewing angle. So in a sense, what's 90 is not projecting to 90, but it's projecting to 90 plus the viewing angle. It's projecting at the person. So this is just very strong data for the projection. The fits are just about as good all over here. All right, so here are the variations, and these again are variations now against the line, which is, so this is 60, 30, 0, minus 30, minus 60. So these are the lines which were the viewing, these are the angles which are the viewing angles. So this is again telling you how everything is rotated. Another way to show this is to plot for each of these views the perceived pose versus the perceived pose in the frontal parallel view. And these are the coefficients of the line of unity, and they're almost 1. And again, what you can see is they're all, the slopes are 1, so they're very, very correlated, but they're shifted up and down by the viewing angle. So this makes us, sorry, and then the model we fit here, is that the next slide or this one? Sorry, this one, is actually this model, but we've allowed one more parameter that I will talk about in a second. So essentially this is making us think that people are using the same rule that they do for frontal parallel viewing, but they are despite the fact that the retinal orientations have changed, and they're not at all taking care of the frame. So the pointing at the viewer thing is pretty simple. These all point at you. Sorry. If you look at the projections, they're all vertical. So if this is vertical when you're looking at it head on, if you go to one side, it's just going to stay vertical. So if it's going to point at you here, it's going to point at you there. Given if you use that you use for scenes, that something that's vertical is pointing at me. So it's like an observer-centric response. So this was the model we had fit before. We needed to put one more parameter here because if you look at this, there's another interesting thing that happens. It almost looks like the ground plane slants down over here. And so we put a little parameter for that. And you can see that that's because of the change in the shapes. And so we put this one parameter. This K0 stays the one that we had over here. So all of these fits. So this was one parameter fit, and this is another second parameter fit, but the first parameter is not changed. So you get all these beautiful fits from these back projection functions without doing much of anything. And this thing about slant changes for the extreme views a little bit, but that's all it takes. So it makes us think, again, that people are using something about the back projection. The other interesting thing here was we decided to look at all the observers. There were 8 observers. And this seems like, and this sort of shows you that this is a very natural task for people to do. So when we took correlations within viewing angles across people, all the people, of their perceived poses, the mean correlation is 0.9934 and the standard deviation is 0.0037. So I've never seen such accordance among people for a complex visual task before. And that makes us think both that this is a very natural task for people to do, and second, that they're all using the same rules. And these are models, the same model fit to each person's data. These are 4 people. You can see these are all pretty nice fits, and these are 4 more people. So there's, as I said, an alternative hypothesis is this frame discounting hypothesis. Our hypothesis is that people use retinal projection in the picture viewing without considering the slant of the picture. Qualitatively different hypothesis would be that they estimate the slant of the screen and apply the correct back projector for that screen. This hypothesis predicts that perceived poses should vary along the unit diagonal, similar to the back projection functions. And we don't see this. We see the systematic shifts that negates this. But there are Nature and Nature Neuroscience papers claiming the frame hypothesis, so we had to do more to show that. So the other thing is, when we did this experiment, we had done it both binocularly and monocularly. And what we found is that so these are the monocular pose estimates, these are the binocular pose estimates. These are again the R-squareds for the lines of unity. And you can see that it's just they're almost perfectly there. There are a few points that point out here. And so there was no difference between binocular and monocular pose judgments, but that made us think that people weren't using anything but the slant of the monitor. But we also did a control experiment where we had people look through a funnel in a dark room, so they actually could not see the frame of the screen. They just could see the objects. And these are data for 0 degrees, minus 30, and minus 60 without any view of the screen. And the model fit is actually from the first experiment for the average. So this is how looking at the screen fits not looking at the screen. So with these 3 things, we just don't think people are paying any attention to the screen. So that was these simple objects. And besides following this from Pearl's team, seeing a picture that had changed a lot, the other reason we wanted to do this was because all the Legos were sort of centered here, the vertex was centered here, and they were all on the ground. When you have real limbs, they're sometimes floating above the ground, they're sometimes elevated from the ground, and they're sometimes not even centered in the center. And all of those things make differences in the retinal projections. And I won't go through these equations, but just to say, off-centered limbs have a different retinal projection. Elevated limbs, when they're raised up from the ground plane, have a different retinal projection. And floating limbs have a slightly different retinal projection. And all of these change the retinal orientation of the limb projection. So, one reviewer for this paper, which is now in its second stage, had this question like, so you have this. What happens if people are assuming that things are on the ground and they're applying your back projection? What kind of systematic differences from the back projection function that you're using would you see? So we calculated that. So here are physical 3D poses, and these would be the perceived 3D poses for different off-center coordinates. So this would be centered. This is 20 units one direction, 20 units the other direction, floating above the ground by these units and elevated, it doesn't really matter, or elevated by an angle like this. And what you can see is the blue is the original back projection function, and you have variations from there. And so we wanted to see if these complex ones give us some of these. So they're the same predicted functions over here, and here are the data from the dolls. And what you can see is there's a lot of variation around 90, and it's in all of these things. There isn't very much variation like over here around 180, and same thing here. There's not very much variation around 180. And so when you look at these off-center limbs, that's where you expect the variation to be. It's around 90. Not around 180. And that's what most of our limbs mostly are, that they're off-center. The floating things don't make that big a difference, and the elevated limbs make a little bit of noise here and here, and that's what's happening over here. But the interesting thing is, even in this much more complex case, when we plot the perceived poses for different views across the perceived poses from the frontal parallel view, you again get these almost perfect lines of unity, and again shifted by the viewpoint. So people are again using the same rule, and what we were showing for the simple cases. And again, the pointing at the viewer thing, well, this keeps pointing at you. If you look at it, it's vertical in projection. It's going to be vertical here. You go to one side or the other side, it's going to stay vertical. So the pointing at the viewer thing is just purely a question of what the retinal orientation is. Again, I want to show you what different observers do. Even if you just look at these are across different observers, you can see how similar they look. And the mean correlation across observers is 0.98, the standard deviation was 0.01. So again, it seems like a really natural task, and people seem to be using the same things. Those first 5 were old observers, these are new observers. Also, these lines being fit are the models from the Legos. And I told you what the variations are from. So to summarize this first part, first set of 3D poses in real scenes can be explained by the hypothesis that observers use a geometric back projection from retinal images with an added frontal parallel bias. The rules of 3D viewing are also used for picture perception. Our model can explain post-perception of deep views of pictures, including the illusory rotation of the picture with the viewpoint. And brains seem to exploit knowledge of projective geometry, either through evolution or learning. So that was the first part. So the second part is geometrical structure of perceptual color space, and this was done by Rob Ennis as part of his dissertation. So mathematical spaces are used in a very large number of sensory, perceptual, cognitive, and other modalities to represent stimuli in a way that people hope will capture something about what is important properties are in some usual tasks. Color is a great place to look at mathematical spaces because, first of all, color spaces date to antiquity. I mean, there are color spaces from Arab science in the 10th and 11th century. Hannah Smithson published a color space that a bishop made in the 13th century. But they really become useful. I mean, Newton published a space. They really become useful with James Clerk Maxwell's experiments, where each point in the space represents a large number of metamers, which is physically distinguishable spectra, but which look identical, which are the same color in a reduced field. And based on Maxwell's work, later work, these are two more modern spaces. This is the CIE space with some fanciful idea of what these colors would look like. And this is the McLeod-Boynton space, which is based on cones, and it's a transformation of this. And because Maxwell showed that color matches are invariant to superposition and multiplication, he also could use the recently invented linear algebra from Grassmann to put it all in a vector thinking. So you can represent colors as vectors in an affine space. But all these spaces show are colors that are indistinguishable. They tell you nothing about how different neighboring colors are from each other or how similar they are. And similarity, color similarity is one of the things I think we do more than anything else in terms of color. We use it to judge whether the objects are the same across the lights. We use it to judge whether two paints are the same. We're using it all the time. So for things like that, McAdam measured these very famous McAdam ellipses. And what these were, was he was doing color matches to the center part, and he just measured across two axes what the variation was. And he sort of tried to capture the variation in terms of these ellipses. And as people like Lagrange and Friel noted, these have a very systematic variation, and there are theoretical treatments to try to explain these. In industry, people looked at these and said, okay, so if you could do some transform of this space, you could turn all these ellipses into circles, you would essentially have a Euclidean metric, a uniform color space. Because then you could, you could go in all directions, and so in an affine space, you can think about ratios in any direction, but angles don't matter because you can stretch one axis versus the other freely. So here's the Farnsworth version of a nonlinear transform, and then there are these two standard spaces called CIE Lab, CIE Love, which are nonlinear transforms of here, claiming to be uniform spaces, and I'll talk about those in a few minutes. A different approach, not based on local discrimination, but just giving people pairs of colors and asking them to rate similarity from 1 to 10, something that it just doesn't sit well with me, leads to cobwebs like this, which are similarity spaces, supposedly. And this is often done using multidimensional scaling, and Taro Indao was a major proponent of that. So the problem with multidimensional scaling was tackled by Sophie Berger, Larry Maloney, and John Kraskoff in 1995, where they used, I won't go into their experiment, but they essentially used proximity judgments to look for additivity of angles, which is what would happen in a Euclidean space, and found marked non-additivity of angles for color proximities. So it meant that you really couldn't embed, by their measurements, color similarities into a Euclidean space. So we know there are hierarchies of spaces. If you can't have Euclidean, you could have affine, which just doesn't have angles, but it does have ratios along the line, parallelism, and ordering. And if you can't have affine, you could have projective. If you couldn't have projective, you could have topological. And it does seem that there's an order to colors. So we said, all right, let's see what we can do about affine spaces. And so in a completely different place, so even though Jan has done things in color spaces, he used his Varigno's theorem for space. So we decided to bring it into color. So what Varigno's theorem says is take any arbitrary quadrilateral. If you join the midpoints of the sides of every quadrilateral, they form a parallelogram. So that's the theorem. And of course, if it's a parallelogram, then if you join the vertices of the parallelogram, which is the same as joining the midpoints of the sides of the quadrilateral, the two lines joining them should meet at both of their midpoints. That's just what a parallelogram is. this was considered a really remarkable theorem, I suppose. That's why it got its name on it. But when linear algebra got invented, and you realize that this was about vector spaces, then it essentially just becomes a test of consistency. Because what it's saying is, you can take any quadrilateral and you represent its vertices as 4 vectors. And then you can make sums of pairs of vectors. You can go this one and this one and this one and this one, or you can go these two and these two. And you divide them by a half, and then you add the resulting vectors. And now you should divide them by a half, and you should get exactly the same vector, because this is just a centroid. Because it's really the same, it's a sum of the same vectors. So it just becomes a test of consistency. But what it does say is that if there's a quadrilateral and Varenius theorem does not hold for it, then you can't represent its vertices as vectors in an affine space. So it becomes a test for an affine space like that. So what Rob did was he set up on a screen pictures like this, with one color here, and the person was asked to independently adjust the hue and saturation of this patch using 2 joysticks to make it the midpoint. And for a midpoint, what we said was set patch B to the color that if all the colors equally similar to patches A and C is the most similar. So that's just the definition of midpoint. And we used, so these are McLeod points and coordinates, don't worry about them. So we used a diamond-shaped quadrilateral in that space and a square-shaped quadrilateral in that space. And these are 4 observers. This is the diamond. This is the square, I think. And so they made midpoints of the sides, and then they made midpoints of the pairs of midpoints. And what you can notice is, first of all, there's huge errors, and sometimes it's just going off in very different directions. And there really is no, so these 2 triangles, pointing up and pointing down, should coincide if this is an affine space. And they're nowhere near coinciding, all right? So this is not an affine space. And that just sounded like completely wrong. I mean, what we know the color matching is an affine space. We know we can order colors, we can do all kinds of things with colors. So how could it not even be an affine space? And then you start thinking, and you say, you know, if somebody hasn't been brainwashed, like all of us have been in perception things, is white any less different from green than red is? They're just 2 different colors. And that's part of what was happening. Some of these people were not thinking of white as a center of the color space. So Hannah Smithson and I had done a study on color constancy, where we had a large number of objects under 2 different lights, and we asked people just for each object, just to say whether it was reddish or greenish, or yellowish or bluish. Very simple task. And that led us, so what we could then do is find the boundary between reddish and greenish and yellowish and bluish. And what we found, it was so systematic that, so in chromaticities they were different, but when you put them in reflectances, they would almost fall on top of each other, which was like a very strong basis for color constancy. And this was just a simple, we weren't telling people what reddish was, greenish was, yellowish was, bluish was. So if people could do something so systematic, there was something wrong with our experiment. So we decided to redo this experiment. And we now said, okay, it's the same surrounding colors. Consider patches A and C in terms of red, green, and blue, yellow qualities. Then consider the change in red, green, and blue, yellow between patch A and patch C. Then set patch B to midpoint in both of these dimensions. We didn't tell them what red, green, blue, or yellow should be. That's completely their discretion. So we used the 2 quadrilaterals we'd used before, and we also used a bunch of smaller ones. So these are around white and the diamonds that we were using, and these are the different illuminants on this side. So this is on one screen, and these are on the other side. And when you combine them, what's coming to the eye are these objects, and they're color-coded with the color of the illuminant. So here are 4 observers, the diamond and the square, and what you can see is there's some variation, but essentially putting very different lights on and pushing them around makes almost no difference. People set the same midpoint, so all we had to do was set the midpoint. And this is with the with the opponent color representation. If you do an opponent color representation, not only do you get an affine space, but it's sort of invariant to adaptation, which is really nice, because what Haddon had shown was essentially color constancy for these categories. But now you can think about the fact that if midpoints are invariant to categories, to illuminants, then any point here is the midpoint of some 2 points on these categories. And if those are invariant, that will stay invariant too. That's illuminant. So essentially that helps us generalize color constancy to the whole space. So then there are these uniform color spaces. And so what we've looked at is really the intrinsic geometry. And I could say something about the extrinsic geometry, but I won't for now. But some of you said, all right, so there are these uniform color spaces, and people use them for all kinds of things. In industry, they use for looking at tolerance, and that's just fine. But people in physiology and people in cognitive psychology often use these spaces to get a number of equally spaced colors which are quite separate, all right? Because they're uniform color spaces, that's how you get them. And if you tell them it's not, then they say no, it's uniform color spaces. So we said, all right, so we have midpoints. We have perceptual midpoints. We can just plot the perceptual midpoints for the representation of each of our vertices in here. And if these spaces are correct, then the perceptual midpoints, which are these squares, should coincide with what the predicate midpoints are, which are these green, these circles over here. And as you can see, they don't. And some places more, some places for some of this, so these are 4 observers. Sometimes they come close, but sometimes they're really off. And so I won't go through the statistics, but when you do the statistics, you really don't want to use the uniform color spaces to think about similarity across widely separate colors. And it's sort of interesting that they've been around for ages, and nobody's actually ever thought about looking at similarity like this. All right, so to summarize the second part, so the geometry of perceptual color space satisfies affine properties only when observers explicitly use an opponent color mental representation. And the thing is, they don't naturally do that. We think 2 of our 4 observers were doing something similar to that, but 2 were completely not doing that. But when you instruct them, they do it. And then this adaptational invariance is very nice because it generalizes color constancy measurements, not just ours, but when people do color constancy, most of it is just adaptation. They do a small sample of points, but now from this thing where midpoints are also being preserved, you can generalize it much more. And uniform color spaces can delimit industrial tolerance of color specifications, but they do not estimate perceptual distance of separated colors or define a set of separated equally spaced colors. So, conclusions. So, this is the age of statistics and big data, but what I learned from John is that geometry retains its power to provide deep insights into visual perception. Whether geometry is innate to the human brain, I won't talk about now, but you can read people all the way from Plato to Berkeley to everybody who's written on it. And another interesting point is whether formal geometry comes out of this knowledge. And there you can read really greats like Poincaré and Einstein. Einstein is actually a really lovely paper on it. And the reason for doing experiments like this is you can actually start bringing some empirical evidence on these questions. So I showed you where people do pretty well with poses, though with a frontal-parallel bias. Well, there are places where we do awful. So this is a building on 2nd Avenue. And when you look at it facing north, the balconies look like everything here is going to fall into the apartment. And when you look at it from the south, it's even more dangerous. It's going to fall on people's heads down here. But these just happen to be parallelogram hexagonal balconies. And the perspective projection that comes into your eyes, we don't know how to account for it. So it's limited. And then there are other places like shape from texture where we're very good at using perspective to get at least qualitative shapes correct. So I think these questions are really interesting, and the more we think about tasks and it looks like doing geometrical tasks is very natural to us, the more we can start answering.